In this video, we are going to do some more proofs about a relationship between sets, in particular subsets and set equality. This time we're going to look at set identities that are a little bit more general. So we're going to review the definitions of what it means to be a subset and what it means for two sets to be equal. We're going to explore a general set identity, try to come up with one, and then we're going to prove our result. So we're going to go through the entire problem-solving process. All right, so just recall, this is the same as from the last video, just so you can review. If A and B are sets, we say that A is a subset of B. If whenever an element is in A, then it is also in B. And we say that A equals B if an element is in A, if and only if it is also in B. So as I mentioned before, both of these statements are for all statements. If you're looking at the subset definition, we're saying that for all x in the universal set, if x is in A, then x is in B. So we're trying to prove that if x is in A, then x is in B, and our overall assumption is x can literally be any element in the universal set. And so when we prove this, we assume x is in A, then we show that x is in B. We do something very similar for when we're proving two sets are equal. For all x in the universal set, x is in A if and only if x is in B. This is going to give us, again, an if and only if statement where x can be any element in the universal set before we start assuming things. And then our proof is we got to do two directions, right? We got to assume x is in A, show that x is in B, then do the same thing the other way around. Assume x is in B, show x is in A. All right, so now let's look for a general set identity where A, B, and C are not particular sets, but they could be any old sets. We're going to have to make some extra assumptions to make this theorem interesting. So what we're going to do is we have three sets A, B, and C, and all we know is that A is a subset of B. And the question I want to know is, what can we then say about A intersects C and B intersects C? What's the relationship? Do they have a relationship? Maybe they do, maybe they don't. All right, well, let's take a look at a Venn diagram just to see if that can give us any insight about what the answer is. Let's not worry about the proof right now. We don't even know what the heck we're proving. All right, so we know that A is a subset of B, which means if I'm looking at that Venn diagram, not every region in that Venn diagram can have actual elements in it. So for instance, that region there that I have, where I have the empty set sign, there can't be anything in there, because if we had stuff in there, that would be elements in A that are not in B, but we're assuming that A is a subset of B. So there can't be anything in that region. There also can't be anything in the region with the other empty set sign, because again, those are elements that are in A but not in B, and you can't have that when A is a subset of B. So if we're looking at what A intersects C is, it's that little region in the middle there, right? That's still in A and still in B, and it's also in C, right? A intersects C, and those are the only elements that remain that are in both A and C. So let's see where B intersects C is. Well, let's see. B intersects C is all the stuff that's in A intersects C, actually, plus perhaps a little bit more if there are any elements in that additional shaded space. So if we're looking at the Venn diagram, what appears to be the case is that A intersects C is a subset of B intersects C. Now, I do want to point out that it may seem obvious that A intersects C is a subset of B intersects C, but that's not always the case. For instance, if I look at that shaded region there, those are elements that are in A intersects C, but not in B intersects C. So this follows from the additional assumptions that we have A as a subset of B. So we need those additional assumptions in order to get that. So in other words, A intersects C is not a subset of B intersects C in general. All right, so let's prove our theorem. Here's the statement of our theorem. Let A, B, and C be sets such that A is a subset of B. Then A intersects C is a subset of B intersects C. All right, so what are we going to assume? Well, we're going to actually assume a couple of things. First of all, our overall assumption from the theorem is that A is a subset of B. But remember, we're also proving that A intersects B is a subset of B intersects C. I'm sorry, A intersects C is a subset of B intersects C. That means we're also assuming that some arbitrary element X is in A intersects C. So we're assuming X is an A intersects C because we're proving a subset proof, and we're assuming that A is a subset of B because that's part of the assumptions of our theorem. All right, and what we want to show is that X is in B intersects C. So we have everything we're assuming. We have everything that we want to show. Let's see if we can work our way there. And once again, I'm going to try to work backwards, at least a little bit. We may have to skip around a little bit, but that's problem solving. So X is in B intersects C, and if I'm trying to imagine the step that comes right before that, my guess is going to be the definition of intersection. So the intersection of two sets means the elements that are in both of them. So if the only way we can show that X is in B intersects C is to show that X is in B and X is in C. So how would we show one of those things? Well, let me see. Actually, X and C is easy. One of the things we're assuming is that X is in A intersects C. Everything in A intersects C is in both A and C. So in particular, it's in C. So that part's fine. Okay. Now the next thing we have to show is that X is in B, and well, we can actually get that from the fact that A is a subset of B, right? So we know X is in A since X is in A intersects C. But since A is a subset of B, that means if X is in A, which we know it is, then it follows that X is in B. So let's see how the logic of our theorem is going to be. So we're going to start with, we know that X is in A intersects C, so we can conclude that X is in A. Since A is a subset of B, that tells us that X is in B. That's our next step. Right, so that's half of the things we need to prove that X is in B intersects C. Then we can say that X is in C because X is in A intersects C, and that's just the definition of intersection. So we've just proven that X is in B, and we've proven that X is in C, which means that X is in B intersects C. So the logic works out. That's a nice outline of our proof, and now all we have to do is make it a little more formal, make it a little more nice for our reader. So we're gonna first of all state what we have to prove in order to get to the end of this proof, right? So to prove that A intersects C is a subset of B intersects C, we assume that X is in A intersects C, and we show that X is in B intersects C, right? So we're setting up what we assume, what we show, so the reader knows what we get to assume and knows what it's going to be like when we get to the end. So from the assumptions of the theorem, we also assume that A is a subset of B. And remember, we're setting this part up because we want to show that X is in C. Or I'm sorry, that X is in A. So since X is in A intersects C, we know that X is in A, but we also have that A is a subset of B, and so X is in B. Right? So we use the fact that we know X is in A intersects C to show that X is in A. We're then using the fact that A is a subset of B, the definition of subset, to show that X is in B. We're halfway there. Next, we have X is in A intersects C. That's by assumption. And so that means that X is in C. So we've just proven that X is in B and X is in C. Nice to summarize those two things because, first of all, there's a lot of things going on, and it's hard to know what's relevant and not relevant. We're pointing out the things that we proved and the ones that are really relevant to our next step, which is since X is in B and X is in C, by the definition of intersection, that implies that X is in B intersects C, which completes the proof. And again, we're letting our reader know that we got to the end. So I do want to say something about Venn diagrams, especially as they appeared in our problem-solving process. They're extremely useful for helping us understand the assumptions of the theorem. We were able to figure out what does a subset of B look like in terms of the Venn diagram. It gives us a nice visual for that. It also gives us a nice visual for helping us figure out what the theorem was that we wanted to prove. We could literally see that A intersects C was a subset of B intersects C from the Venn diagram. One thing it was not useful for, as it turns out, was the proof itself. But we shouldn't get too upset about that. There's so much that it was useful for that the fact that it's not useful in the proof itself I wouldn't not even say that's a huge weakness about Venn diagrams. It's just that Venn diagrams can't do everything for us. Just remember, for the proof itself, we need to use the formal definitions. We can't just say, look, the Venn diagram commands me to say that this theorem is true. We got to do it from the definitions and from and using logic. All right, so now I've got a few abstract set identities for you to prove in the activities. The name of those activities is a PDF file called proving abstract set identities.